So this is the 24th session on rigid body kinematics. This is in continuation of the 23rd video. So in this we are going to take up the some more theory on acceleration equation for rotating rigid body. Okay. But before I go ahead, I would like to make one thing very clear. You see, the videos which I am making, they are meant for complete. You can study all entire theory from this video itself. You don't have to go to any other coaching institute. Okay. You don't have to go to join any other coaching institute. By studying this video itself, your theory will be and numerical will be complete. If you understand this theory and the problem which I take in this, if you go through them, then you solve problem for any other book or source, you will be able to solve most of them. And in case you have difficulty, you give the difficulty in the comment box. I have to solve it and communicate to you. Okay, fine. All right. So before going ahead, I'll discuss one more aspect on the SRC procedure for acceleration as was given in the 23rd video. So see, it's like this. Suppose F is some given reference frame, M is some rigid body in plane motion with respect to F. It is in plane motion with respect to F. Okay. Suppose omega is the angular velocity of M with respect to F taken to be anti-clockwise, just for the sake of argument. Suppose beta is the angular acceleration of M with respect to F taken to be again anti-clockwise with respect to F. Now P1 and P2 are two locations of M in the same base plane. This is the distance R. This is the line joining P1 P2. R is the distance between P1 and P2. R is the distance between P1 and P2. Okay. Now suppose velocity of P1 with respect to F is V1F and acceleration of P1 with respect to F is A1F at a given instant. Suppose velocity of P2 is with respect to F is V2F and A2F is the acceleration of P2 with respect to F at time t. Okay. Suppose this angle is psi 1 and this angle is psi 2. And suppose this angle is theta 1 and this angle is theta 2. Okay, fine. Now, P1 and P2 are two locations of M, real or imaginary, any one of them. So, distance between P1 and P2 is fixed. Okay. Now, suppose unit vector from P1 to P2 is E1 hat. E1 hat is a unit vector from P1 to P2. Okay. E1 hat is a unit vector from P1 to P2. Like this. I just show the diagram here like this. See. This is P1. This is P2. This is a unit vector E1 hat from P1 to P2. And this is a unit vector E2 hat corresponding to sense of beta at right angles to line P1 P2. Okay. So what I do first, I apply the SRC procedure for acceleration between P1 and P2. SRC procedure for acceleration between P1 and P2. So, SP arrow P1, P1 is the selected point, OP arrow P2. Alright, SP arrow P1, OP arrow P2. I draw the line joining SP and OP whose orientation is same as in the problem. So, orientation is like this, so I draw the line with this line here. This is P1, this is P2. Now what I do first action, I give the acceleration of selected point P1 to other point P2. Acceleration of P1 with respect to F is A1F. So I give acceleration A1F to P2 at an angle of theta 1 with the line joining P1, P2. Now next, rotation term. I write down the sentence, omega is a clockwise, so P2 moves in a clockwise circle with P1 as center and radius R. So I give two accelerations to P2. I give an acceleration omega square r to P2 directed towards selected point P1 and we give an acceleration r beta to P2 normal to line P1 P2 corresponding to sense of beta. Beta is like this anti-clockwise, so r beta should be in this sense. Now net acceleration of P2 with respect to F is a vector sum of these three terms. So I'll write down like this. A2f, acceleration of P2 with respect to f at time t, is the vector sum of this, this and this. So this will be equal to A1f plus r beta along unit vector E2. So this will becomes r beta E2 hat. And this omega square r is opposite to E1. So it is minus plus omega square r into minus E1 hat plus. Okay, fine. Now A1f, what I'll do, I'll break it up. A1f I'll resolve into E1, E2. So A1f will be written as, this A1f will be written as A1f cos theta 1 into E1 hat plus A1f sin theta 1 into E2 hat plus r beta E2 hat plus omega square r into minus E1 hat. Now acceleration of P2 is what? A2f. It makes an angle of theta 2 with this line. This also I'll write down in E1, E2 notation, unit vector notation. So this A2f will be written as A2f cos theta 2 E1 hat plus A2f sin theta 2 E2 hat. Okay, this is equal to this term. This E1, E2 I'll make common, E2 also I take common. So this becomes E1f A1f cos theta 1 minus omega square r into E1 hat, and this becomes E2 hat. This becomes plus A1f sin theta 1 plus r beta into E2 hat. Okay, fine. So this I'll rub, okay. This one I'll rub, okay. So now E1, E2 are linearly independent unit vectors. So this equation is going to valid only when respective coefficients of E1 hat, E2 hat on both sides are equal. So I equate the coefficient of E2 hat and E1 hat both sides. First I equate the coefficient of E1 and E1 hat. So what do we get? A2f cos of theta 2 is equal to A1f cos of theta 1 minus omega square r. And what if we equate the coefficients of E2? Then A2f sin theta 2 is equal to A1f sin theta 1 plus r beta. Okay. So see, this when simplified, beta gives how much? A2f sin theta 2 minus A1f sin theta 1 by r. So this I'll rub here, okay. Now see, what is this A2f sin theta 2? A2f sin theta 2 is the component of A2f normal to P1 P2. And what is A1f sin theta 1? A1f sin theta 1 is the component of A1f normal to P1 P2. And what is this difference? This is called the relative normal acceleration between the points P2 and P1. So in plane motion case, beta will be written as relative normal acceleration. Relative normal ACCN meaning acceleration by separation r. So relative normal acceleration by separation r. That is what is beta. So beta becomes relative normal acceleration by separation r. This is beta. Now this corresponds to which formula? Omega is equal to relative normal speed by separation, as we did in the which video? In the second video. Yes, second video. Yes. Omega is equal to relative normal separation, relative normal velocity by separation. This corresponds these two analogous formulas. I hope this we remember. This I will discuss in great detail. Okay. In second video also the proof of this was given. So omega is equal to relative normal velocity by separation, and beta is equal to relative normal acceleration by separation. Okay, this I'll wrap this one. Okay. And one more thing, see, we know that distance between P and P2 is fixed because there are two locations of a rigid body. So we know from previous videos that component of V1F and V2F along P and P2 should be equal. So what do we get? V1F cos theta 1 is just equal to V2F cos theta 2. This is also discussed in the first video on the relative velocity. You go there, you'll get it. So V1F cos theta 1 is equal to V2F cos theta 2. This was fully discussed. I hope you know it. But see, if we see this term, this what we will do? Component of V2F and V1F along E1 hat along line P and P2 should be equal. But see, for acceleration, you see they are not the same. See, you can see this. This and this are not the same because of this term. This I'll write as A1F cos theta 1 is equal to A2F cos theta 2 omega square r. Okay. So this time you can see that they are not the same. A1F cos theta 1 is not equal to A2F cos theta 2 because of this additional term. So what does this mean? See, it means that, see, what I am saying is, if distance between two moving points P1 and P2 is constant, then at any instant of time, component of velocities of P1 and P2 along line joining them must always be equal. But the same result cannot be said for accelerations. If P1 and P2 are two moving points, then it doesn't imply that acceleration of P1 and P2 along line joining them must also be equal. They are not the same because of this additional term, because of this omega term, angular velocity term. That is rotation of the body. So because of rotation of the body, acceleration of P1 and P2 along common line joining them is not the same. But velocity of component of P1 and P2 along line joining them is always same. If one more case, if omega is 0, body is not rotating or instantaneously it is not rotating, then this term goes away. In that case, A1F cos theta 1 becomes equal to A2F cos theta 2. This point should be cleared. See, so what I'll state it again in view of its importance. Importance is this, that if distance between two moving points P1 and P2 is constant, then at any instant of time, component of velocities of P1 and P2 along line joining them are always equal. But the same result cannot be said for acceleration. If P1 and P2 are two moving points such that the distance between these 2 points is constant, then it doesn't imply that component of accelerations of P1 and P2 along line joining them are also equal. They need not be equal. They differ because of this term. If omega is 0, the body is instantaneously not rotating. Angular velocity of body is 0 at certain instant. Then these terms become equal. So we can state this another way. If distance between two moving points P1 and P2 is constant, then component of relative velocity of P2 and P1 along line joining them is always 0. But for acceleration, this statement need not be true. Okay, fine. This I'll grab it now. Fine. So we'll say this way. If distance between two moving points P1 and P2 say is constant. Distance between two moving points P1 and P2 say is constant. Then two things we can say. First, component of relative velocity between these 2 points along line joining them is always 0. Component of relative velocity, component of relative velocity between these 2 points, along line joining them is always 0. But second, component of relative acceleration between these 2 points along line joining them need not be 0. Okay, this is a vital concept. Okay, fine. So what I have said in this, if distance between two moving points is constant, then component of relative velocity between these 2 points along line joining them is always 0. But the component of relative acceleration between these 2 points along line joining them need not be 0 because of this additional rotation term omega square r. If omega happens to be 0 instantaneously or permanently, then again this equation will be valid instantaneously or permanently. Then these two acceleration terms will be equal along line joining them. This point I have made it very clear. You should be clear with this term, okay? So this point should be understood very clearly. Okay, fine. So this should be understood very clearly. If you take this into account, then it's all right. Fine. So this was the 24th session of rigid body kinematics. Okay. So this I fully discussed. I hope it is clear. Now what I do, I'll pass over to some numericals. Okay. I'll pass over some numerical problems on this rigid body kinematics for acceleration equation. All right. So this I'll wrap it. This I'll wrap it now. Okay. So, I'll take up some numerical problems on SRC procedure for acceleration. Okay, fine. So the question is this. This is the question. Numerical problems on SRC procedure for acceleration. Okay. So, question I'll write here. So P1, P2 is a rigid rod meter which rotates in a vertical plane with respect to ground, G for ground, okay. All the details are shown in the diagram. All the details are shown in the diagram, okay, along with the coordinate system. Along with the coordinate system, okay. In each case, find the acceleration of P2 with respect to ground in I hat j hat notation. I hat j hat notation, okay. I hat j hat denote the respective unit vectors along x and y axis. All right. So now coordinate system is given in all the cases. Orientation of this coordinate system is as usual. X axis rightward, y axis upward, okay. So part A is this. This is the rod P1, P2, okay. Length of rod is 2 meter, constant, rigid rod. Rod is given to be rigid. Acceleration of P1 is 10 meter per second square with respect to ground at right angles. Omega is 4 radian per second with respect to ground. Beta is 3 radian per second square with respect to ground. So omega is the angular velocity of rod with respect to ground, and beta is the angular acceleration of rod with respect to ground at this instant. Then we have to determine a acceleration of P2 with respect to ground at the given instant. So we will follow the SRC procedure for acceleration. The selected point is P1, other point is P2. P2 is the other point, P1 is the selected point. We draw the line joining SP and OP, whose orientation is same as in the problem. This is the vertical line, this is P1, P2, okay. Now what we do, give the acceleration of selected point P1 to other point P2. So we give 10 meter per second square to P2, okay, right angle direction, okay. Now we write down the sentence. Omega is clockwise, beta is also clockwise, both are clockwise. So P2 moves in a clockwise circle with center at P1 and radius 2 meter. So 2 acceleration should be given to P2. Omega square r to P2 towards the selected point P1. Now omega square becomes 16 into 2, 32. 32 meter per second square downward direction. And r beta. Beta is clockwise. So r beta means becomes how much? 2 into 3, 6. So 6 meter per second square rightward. The acceleration of P2 with respect to ground is the vector sum of these three terms. So we'll write as A2G equal to 10 I hat. This is on x-axis. 10 I hat plus 6 I hat. And this is on minus j. 32 into minus j. So this becomes 16 I hat minus 32 j hat meter per second square. Okay. So A2G becomes how much? 16 I hat minus 32 j hat meter per second square. This is therefore the required answer. Alright. So this becomes 16 I hat minus 32 j hat meter per second square. Alright, fine. So this I'll rub it now. So part B of the question is this. This is again a rigid rod P1, P2. Length again 2 meter. Acceleration of P1 is rightward. 8 meter per second square with respect to ground. Since omega is clockwise, 5 radian per second with respect to ground. Angular acceleration is also anti-clockwise with respect to ground. 2 radian per second square. Coordinate system is same as here. Part A. I'll draw the coordinate system here also. Now we have to find A to G. Again we apply the SRC procedure for acceleration. So P1 becomes selected point is P1. SP arrow P1. and OP arrow P2. See, SP left or P1 left doesn't matter. Whatever meaning should be clear. Now I draw the line joining SP and OP, which is vertical. So I've drawn the line here also. P1 and P2. Okay. Now what I do next? I give the acceleration of P1 selected point P1 to other point P2. So I give 8 meter per second square towards rightward direction. Alright. Now I write down the sentence. Sentence is what? Sentence is this. P2 omega is clockwise. Beta is anti-clockwise. So P2 moves in a clockwise circle. With P1 as center, radius 2 meter. So 2 accelerations have to be given to P2. To P2 we have to give 2 accelerations. 2 accelerations should be given to P2. First is what? Omega square r to P2 towards selected point P1. Omega square becomes 25 into r, 50. So we give 50 meter per second square to P2 towards P1. And r beta. Now beta is anti-clockwise. So P2 we give r beta becomes 4. Anti-clockwise beta means center this, r beta anti-clockwise, r beta should be left. R beta should be left 2 into 2, 4. 4 meter per second square, okay. Now this is the 3 terms. If you add these 3 vectorially, we get acceleration of P2 with respect to ground, okay. So A2G becomes this one. This becomes 8I minus 4I. 8I hat plus 4 times minus I hat. And this is minus J hat. 50 into minus J hat. So this becomes 4I hat minus 50 J hat meter per second square. This is therefore the required answer. Fine. Alright. So this I'll rub it now. C is this. This is line P1, P2. Now P1 is up, P2 is down. Again, coordinate system is the same as in the part A and part B. This is again 2 meter. 2 meter is the length of the rod, P1, P2. Acceleration of P2 to right angle, 4 meter per second square. Omega is clockwise, 5 radian per second. Beta is also and clockwise 6 radian per second square. Now we have to determine the acceleration of P2 with respect to ground. Again we apply the SRC procedure for acceleration between the points P1 and P2. Selected point becomes P1, other point OP becomes P2. Now we draw the line joining SPOP, that is line joining P1 P2, which is simply this line itself. Now what do we do next? We give the acceleration of selected point P1 to other point P2. Acceleration of selected point P1 is 4 rightward. P2 also we give what? 4 meter per second square rightward. Now I write down the sentence. Omega is clockwise. So P2 moves in a clockwise circle with P1 as center and radius 2 meter. So 2 accelerations have to be given to P2. Omega square r to P2 towards the selected point P1. Omega square becomes what? 25 into r becomes what? 2, 50. 50 up. Omega square r to P2 selected other point P2 towards selected point P1. 50 meter per second square upward direction. Now beta is clockwise. So we have to give r beta to P2 such that r beta is in clockwise sense. Now for r beta to be in clockwise sense, P1 is center and P2 has r beta in clockwise sense. So P1 is here, P1 center, P1 is here. And P2 should give r beta clockwise sense. R beta should be in leftward direction. 2 into beta, 12. Then only it will be clockwise. Okay, fine. Now acceleration of P2 with respect to ground is the vector sum of these 3 terms. Alright. So what do we write? A2G is equal to 4I hat minus 12, 4I hat plus 12 times minus I hat plus 50J hat. So 4I minus 12I becomes what? Minus 8I hat plus 50J hat meter per second square. This is the answer to the third part C of the question. Alright, fine. So how much is A2G? A2G becomes how much? Minus 8I hat plus 50J hat meter per second square. Okay. This is the acceleration of P2 with respect to ground in part C of the question. Fine. I got this one, okay? Now part D of the question is this. This is P1. This is P2. 2 meters is the length of the rod. Acceleration of P1 is given to be 8 meter per second square rightward. Omega is given to be 6 radian per second clockwise. And beta is given to be 4 radian per second square anti-clockwise. Now we have to determine the acceleration of P2 with respect to ground in IJ notation. Coordinate system as again same as in part A, B and C. So again SP being selected point becomes P2 and OP becomes P1. Now we draw the line joining SP and OP, that is the line P1 P2, which is simply vertical. So P1 P2 is like this. Now we give the acceleration of selected point P1 to other point P2. So we give 8 meter per second square to P2 leftward direction. It is right angle to line P1 P2. 8 meter per second square in leftward direction. Now we write down the sentence. Aside here SP just written calculation mistake. Okay. Now we write down the sentence. Sentence is this. Omega is clockwise. So P2 moves in a clockwise circle with center at P1 and radius 2 meter. So two accelerations are to be given to P2. Omega square r. 6 square 36 into 2, 72. So I give acceleration of 72 meter per second square to P2 towards P1. Now R beta. Beta is in anti-clockwise sense. Now for R beta to be in anti-clockwise sense with P1 as center and P2 in a circle, R beta should be in this sense. Then only anti-clockwise like this. Anti-clockwise this way. So R beta. 4 into 2, 8. 8 meter per second square. Alright. So acceleration of P2 with respect to ground simply becomes vectors of these three. This is 8i, this is 8 minus I. This to cancel out. 8i hat 8 times minus I hat plus 72j hat. This comes cancel out. This becomes 72j hat meter per second square. Alright. This is therefore the required answer. So this was the 24th session of rigid body kinematics. Okay. So in this first I told you that about relative velocity concept, okay. Distance between two moving points is constant. Then velocity of these 2 points on a line join them is always equal. But same thing cannot be said for acceleration. There will be true for acceleration also provided omega is 0. At that instant permanently, okay. And one more thing, I derived that formula for beta, relative normal acceleration by separation. That was analogous to what? Relative normal speed by separation. Okay. So there is a similarity and there is also a difference. Okay. So this I close it here. In next session also I'll take up some more problems on rigid body kinematics. Okay. So carefully go through this. Okay. If you understand this, you just take a problem for any other book, any other sorts whichever you would consider fit, you solve them. In case you have some difficulty, you put your difficulty in the comment box. I will solve the difficulty and explain it to you. Fine. Alright. So this close it here.